Can you put the... Oh, okay. Hello, everyone. So first of all, let me begin by thanking the organizers for the invitation. It's a great pleasure and honor to be here. The title of my talk is Light Towers of States in String Theory. And it will be based on 3 papers. I'll briefly mention 2 papers, one with Thomas Grimm and Irene Valenzuela from last year, one with Daniel Clever and Dieter Lust from last year, and most of the talk will be about a recent paper with Dieter Lust and Kumrun Waffer. And the 3 papers are on different topics, but they are unified by this theme of light towers of states. So I hope the talk will hold together. So infinite towers of states are a fundamental and ubiquitous aspect of string theory. They appear all the time. And by a tower may be characterized by a certain mass scale, m, such that the nth state in this tower is at mass n times m. So m characterizes the mass scale of the whole tower. And then what do I mean by a light tower of states? I mean a tower of such states such that in the Einstein frame, the ratio of the mass scale of this tower to the Planck mass goes to 0. So that's what I mean by light tower of states. It's important that you talk about the ratio with respect to the Planck mass. It may be that m doesn't actually go to 0, but the ratio to the Planck mass does. So that's what I mean by light tower of states. And this talk will be concerned with the question, when do light towers of states arise in string theory, or even perhaps in some more general notion of quantum gravity? And of course, that's interesting both from a more formal perspective as to what are these towers of states signaling, what is their role, but also potentially from a phenomenological perspective, because by definition, a light tower is one such that its mass scale is far below the Planck scale, and so in principle may have some observational signatures. So there are 2 by now quite well-known proposals for when you might get the light tower of state in any kind of string theory setting. One is called the weak gravity conjecture, or more precisely, some refinements of it over the past few years are suggesting that there should be a light tower of states such that the ratio of this mass of this tower to the Planck mass is set by the gauge coupling of a U1 gauge field in your theory. So if you take a U1 gauge theory and you make it weakly coupled, you get a light tower of states. That's what the conjecture says. And another one is called the distance conjecture, which says that you get a light tower of states whenever you have a scalar field in your theory and you give the scalar field a large expectation value. So by large, I mean larger than the Planck mass. In that case, the tower of states, in fact, becomes exponentially light. So these are called conjectures. There is no proof of them. Nonetheless, there's been a lot of work over the past few years testing these ideas in string theory and thinking about them more deeply, and so far they've passed every test. And I think it's worth taking them seriously enough to think a little bit about what it could mean if these things are true. So this distance conjecture was proposed based originally on some simple examples in string theory that seem to be satisfying it. But more recently, it's been tested to greater extent. So I wanted to briefly discuss some work that we did on this topic. In particular, we wanted to test it on some highly non-trivial scalar field space. So we thought about, we looked at type 2B string theory on Calabi-Yau manifolds, and we looked at the complex structure moduli space of this Calabi-Yau, which means in the effective n equals 2 4-dimensional theory, the vector multiplet moduli space. And the states that we were looking for, this tower of states, are BPS states, and they will be D3 branes wrapping 3 cycles, and their mass is controlled by these complex structure moduli. And because these are BPS states, these states are labeled by a certain charge vector, which tells you what their charges are under the gauge fields in the vector multiplets. Or if you like geometrically, they tell you what are the wrapping numbers of the D3 branes. And once you specify that charge, you know the mass of these states. It's just given by the central charge formula, which is given by this charge vector contracted into what's called the period vector, which is a function of these complex structure moduli. And this period vector is very complicated for an arbitrary Calabi-Yau, which can have a 100-dimensional moduli space. This would be a very complicated object. But if you know it, you know not only the mass of these states, but you also know the geometry on the moduli space, because it also determines the Kähler potential for that moduli space. So we wanted to see if we can argue for this distance conjecture very generally for any Calabi-Yau moduli space and any infinite distance locus. And at first this might seem like a very difficult task because these are very complicated spaces, but it turns out that there is a very deep and powerful mathematical theorem which does exactly the job that we want. It's called the nilpotent orbit theorem. And what the theorem says is the following. If you take an infinite distance point in this moduli space, so some point far away near an infinite distance, let's call this t equals plus I infinity, then that point will be a singular point in the moduli space, and there will be a monodromy about it. So that means if you go around it, this period vector will transform with some integer matrix acting on it. That's the monodromy about this period vector. And you can take this monodromy matrix and take the log of it and make another matrix, which I call n. And the nilpotent orbit theorem tells you that if you know this monodromy matrix, then you basically know the local behavior of the moduli space as you approach infinite distance. It tells you that the period vector must take this form, so it has to look like an exponential in this monodromy matrix times this parameter, which parameterizes the infinite distance, contracted into some vector which doesn't depend on this distance parameter. So it's essentially a constant, plus exponentially small corrections that are like the instanton corrections, if you like. And now, once you know this theorem, and once you know that the period vector has to take this form around any infinite distance locus in moduli space, then you're pretty much done, because you just take this and you put it into this BPS formula and into the scalar potential. So this tells you how to measure the distance, because you know the metric, and this tells you the mass. And it's easy to show that indeed the distance conjecture that you get a tower of BPS states becoming exponentially light around any infinite distance locus and any Calabi-Yau moduli space just follows straight away from this. Now I should say it doesn't quite prove the conjecture, because what it tells you is a would-be BPS state would become exponentially massless, but you have to show that that BPS state is in a spectrum, and we give arguments that that's indeed the case for many, although not all possible infinite distance loci. So I think this is strong evidence for the distance conjecture, but I should say we generalize this analysis to multi-parameter infinite distances, so rather than just one variable, two variables going to infinity. And there's been a lot of work over the past years analyzing various kind of infinite distance loci in string theory, and they all seem to be consistent with the conjecture. But the main reason I wanted to point this work out is that it possibly suggests what could be the microscopic physics behind the distance conjecture. Why is this happening? And the idea is the following. These states that are becoming massless, these VAP-D3 branes, are known to already have been integrated out into the moduli space. So a very famous example that's at finite distance is the conifold singularity. So the conifold singularity can be understood as one of these D3 branes having become massless, and the geometry in the moduli space near that singularity is determined by the fact that this D3 brane became massless. And now what this analysis that we did for the infinite distances suggests is that you also think of infinite distances as singularities in the moduli space, and they also have a monodromy about them. And so it's very natural to suggest that those singularities, just like the conifold, are caused by integrating out the D3 branes that become massless at infinite distance. Except this time you don't integrate out a single D3 brane, but a whole infinite tower of D3 branes. That would match the nilpotent orbit theorem, which tells you that the geometry of the moduli space is almost completely determined by the monodromy, which is something that's induced by the massless charged states. So if this is true, I think it suggests a very fascinating possibility that the infinite distance loci, or the non-compactness of the moduli space, is actually caused by integrating out the towers of states at infinity. So this would explain what the distance conjecture is really capturing. It's not that there is some kind of connection necessarily between infinite distance and light towers of states. It's that the light tower of state induces the infinite distance. You wouldn't have the infinite distance if it wasn't for the light towers of states. So I think this is a very fascinating possibility, and it would be nice to develop it further. So let me move on to the second topic, which seems very different, but we'll see is actually unified in many ways. And that is, in the second paper, we considered massive spin 2 particles. So a massive spin 2 particle has 5 propagating degrees of freedom, and you can decompose these 5 degrees of freedom into helicity modes. So the 5 degrees of freedom can be grouped into 2 degrees of freedom in the helicity 2 component, 2 degrees of freedom in the helicity 1 component, which is like a gauge field, a Stuckerbird gauge field, and 1 degree of freedom in the helicity 0 component. And since a massless spin-2 field only has 2 degrees of freedom, just the helicity 2 modes, it must be that the kinetic term for these lower helicity modes come from the mass of the spin-2 field. And indeed, if you write down the field's Pauli mass for the spin-2 field, then you see that this gives rise to the kinetic term, and in particular to the kinetic term for this helicity 1 mode, the gauge field inside it. And so, what we see is that the gauge coupling for this gauge field depends on the mass of the spin-2 field. So that's quite interesting. And to determine the gauge coupling fully, you also need to specify how the spin-2 field couples to some tensor. So the spin-2 field will couple to a tensor, not necessarily the energy momentum tensor. And this interaction will always be suppressed by some mass scale, which sets the strength of this interaction. So in the case of gravity, the graviton will couple to the energy momentum tensor, and this would be the Planck scale. But it's a general coupling. And then it can be argued, and I think we did convincingly so, that once you know the interaction strength, normalization, and the kinetic term, you can read off the gauge coupling of this Zuckerberg U1 field inside the massive spin-2 field. And this gauge coupling is just given by the ratio of the mass of the spin-2 field to its interaction mass scale. And one can indeed check that the field will decouple from everything else if you send this MW to infinity, as you expect, or also if you send the mass of the spin-2 field to 0, in which case it becomes pure gauge. Now, once you have this, there's a very natural thing to do then, which is just apply the weak gravity conjecture for this gauge coupling. So we have a gauge field. It's a Zuckerberg gauge field, not a normal one, but still, you can just apply the weak gravity conjecture to it, and then you recover what we call the spin-2 conjecture. And it tells you that there should be a light tower of states, just as before. And this light tower of states should be set if you have a massive spin-2 particle in your theory by the ratio of the mass of the spin-2 field to its interaction mass scale. So that's what we call the spin-2 conjecture. And indeed, it can be checked that this is satisfied, at least to my knowledge, in all known string theory settings. For example, Kaluza-Klein modes, Kaluza-Klein gravitons are massive spin-2 fields, or string oscillators, and they all satisfy this behavior. And once you have this, it's very tempting to say, well, what happens if the massive spin-2 field is the graviton itself? So what would happen if the graviton was massive? So this is theoretically possible, in which case the interaction max scale is just a Planck scale, and so you just recover what we call the strong spin-2 conjecture, which is that if the graviton itself is massive, then there should be an infinitile state whose mass scale is set by the mass of the graviton. And this is very interesting, I think, because potentially in our universe, the graviton could actually have a mass. I think the strongest model-independent bounds come from gravitational waves, and this seems to be the bound, 10 to the minus 22 electron volts. And so if this conjecture is true, it makes a very sharp prediction that in our universe, in fact, the graviton must be exactly massless. So that's a falsifiable prediction, otherwise there wouldn't be a bound like this. So, and I believe it's very universal to any kind of string theory setting. Or it could be that there is, in fact, an infinitile state that's spectacularly light, but I'm not sure if this is actually phonologically viable. Either way, you find a kind of testable prediction. So in that sense, I think it's interesting. So let me move on to the final, to the second half of the talk. So in the last paper, we thought about the following question. Could it be that there's an infinitile state whose mass is set by the magnitude of the cosmological constant? So I already gave various examples where we think you might get a light tower of states. Could it be that you get a light tower of states whenever the magnitude of the cosmological constant goes to 0? So in string theory, the magnitude of the cosmological constant just means the minimum of the potential. And of course, there are many situations in string theory where you find such a correlation. For example, if you just decompactify the extra dimensions, then any energy sources scale away, and you send the cosmological constant to 0. On the other hand, there are Kaluza-Klein modes of the extra dimensions that also go to 0. So there is a correlation between the lambda going to 0 and an infinitile of states becoming massless. But what we try to think about is, could we give some arguments why we might expect such a connection generally? And what we thought of is the following. So let's go back to the distance conjecture. Remember, I said if scalar fields have large kinetics, go large distances, then you get light fields. So what does this mean more precisely? Consider this scalar field kinetic terms. Then this Pij is the metric on the scalar field space. And you can use this metric to measure a proper distance in this field space along some path that's labeled by some parameter tau. And then the conjecture says that if this proper distance is much bigger than 1 in Planck units, there should be an infinite tower of states with a mass scale m, such that at the end point of the path, this tower of states is exponentially smaller than at the beginning point of the path. That's what the conjecture says. So what we said was the following. Well, actually, let's think of these scalar fields as moduli fields in string theory, as I just talked about before. And what is this really actually saying, this distance? Since the modular fields are they're just changes in the metric of the internal Calabi-Yau. So this distance in field space is actually a distance in metric space of the Calabi-Yau. And in fact, you can rewrite things this way. And now you see this is really a variation of the metric. You can write this, in fact, in terms of the 10-dimensional metric. So it's a variation of a 10-dimensional metric. And then you use the metric itself to measure the distance on the field space. So the analog of this is just actually using the metric itself. So this is actually a well-known notion of distance on metric space. You can use the metric itself to be a measure on metric spaces. And this is just capturing the fact that when we move in scalar field space, we're actually just changing the metric of the Calabi-Yau. And so this 10-dimensional formulation suggests that a kind of slight generalization of the distance conjecture which we made, which is the following. Consider being on a manifold that's some external d-dimensional homogeneous space times some internal space, and then go to the Einstein frame of this external homogeneous space, so like de Sitter, anti-de Sitter, or Minkowski, let's say. Then there should be an infinite tower of states that becomes exponentially light as a function of this whole 10-dimensional distance measured by the path that you move in metric space. If you change the metric of a Calabi-Yau, that just reduces to the usual distance conjecture. So it's just a rewriting in some sense of the usual distance conjecture. Now, I should say this expression is not quite general. It's true for transverse traceless metric variations. If you do a trace variation, in particular if you do a Walvis scaling of the internal manifold, then you have to work a little bit harder to go to this Einstein frame. But nonetheless, the point is this. When you look at the kinetic term for the Wahl transformation, it goes like tau, where tau is the exponent here in the parameter, times some order 1 factor. So in other words, the distance in metric space of Weyl transformations goes as tau, the proper distance. And that's all we'll actually need to use. And so what we said was the following then. Well, that's very nice. So distance conjecture tells you cannot vary the metric an infinite amount without something happening. But string theory is a 10-dimensional theory. It shouldn't really differentiate between the internal metric and the external metric. And so maybe it makes sense to apply the distance conjecture to the external metric also. So if we do that, let's think about, for example, ADS space. Then this has this Wahl factor out in front, which is directly related to the cosmological constant. And now we see that the flat limit of ADS space, or in other words, when lambda goes to 0, is in fact an infinite distance in metric space. And we can be a little more quantitative about it. The distance goes like tau, remember, for Walvis scaling, so it goes like log of lambda. So the conjecture will tell you there's an infinite tower of states whose mass is set by the exponential of the distance, which is then power law in lambda. So this is the result one would get from this kind of logic. So the argument is in substance very simple. It just tells you if you take ADS space and you go to the Minkowski limit or the flat space limit, you are moving an infinite distance in metric space. And from all the examples we know in string theory, when you move an infinite distance in metric space, you get light towers of states. Now I should say a word of caution. We're not really sure how to implement the Einstein frame condition when we're doing this variation in the external metric rather than internal metric. So this is to do with something, what this value of this alpha is, but I don't think it changes things qualitatively. You can look at the paper for a lot of discussion about this subtlety. So this argument, as well as examples of string theory, which I'll discuss, led us to propose the following conjectures. The ADS distance conjecture says that if you have an ADS-D space in quantum gravity, then there's an infinite tower of states whose mass scale m, as lambda goes to 0, behaves in this way. So it behaves as some power law in lambda as lambda goes to 0. And the distance argument suggests that this should be true not only for anti-de Sitter, but even for de Sitter spaces. Again, you can just, this distance that you measure in moving metric space is also infinite. And then we also suggested a strong ADS conjecture, which is that if this ADS is supersymmetric, then in fact this per alpha is 1/2. So 1/2 is a very special value. It means that there's no separation in mass scales between the ADS mass scale and the mass scale of this tower of states. And if this tower of states are Kaluza-Klein modes, it's telling you there's no separation of scales between the curvature of ADS and the curvature of the internal space. This is known as no separation of scales. And one might argue, one might think, why could there be an argument for no separation of scales? And we connected it to a different kind of argument that's been mentioned in the swampland, which is that it could be related to an obstruction to having an unbounded number, unboundedly large gauge group in space-time. So it's known in string theory, whenever you have a Minkowski space compactification, the rank of the gauge group is bounded. So you can make it very large, you can get a huge gauge group, but you can't make it arbitrarily large. You can't get SU 10 billion. In ADS space, that changes. So for example, you take M theory on ADS 7 times S4 over ZK, and then this gives you an SUK times SUK gauge group, and you can make this K as large as you want. So ADS space seems to have this qualitative difference from Minkowski space. You can make gauge group as large as you want. But on the other hand, if you think about it, actually it's perfectly consistent with this conjecture in the following sense. This gauge group is propagating on this ADS, but the curvature of this ADS is not separated from this curvature of this S4. So in fact, this manifold should never really be thought of as an ADS space. It just has an ADS factor in it. And therefore, these gauge fields are not really space-time filling, but they are localized on a defect. And it's perfectly fine to have as large gauge group as you want localized on a defect. And so this suggests that this lack of separation of scales may be connected to this kind of censoring, and suggests that in quantum gravity, you shouldn't really have flat limits when ADS-D space goes to Minkowski D, but rather always ADS-D should go to Minkowski D plus P. So there should be some other external dimension, and this would explain also the conjectures. So what is the evidence on string theory for these conjectures? So as far as I know, there are no 10-dimensional or 11-dimensional counter-examples to the conjectures, and there are many infinite sets of examples which do satisfy them. The arguments exist for no separation of scales, so that means alpha equals a half in supergravity. So it's a kind of Malacena-Nunes no-go theorem that tells you need some stringy ingredients if you want to have separation of scales, like orientifolds. The strong version of the conjecture, which says no separation of scales for supersymmetric ADS vacua, is violated by type 2a compactifications on a Calabi-Yau with flux. However, it's known that these compactifications are not 10-dimensional solutions, and so this could be perfectly consistent with the conjecture if, when you uplift them to actual 10-dimensional solutions, you will find that this separation of scale goes away. Both conjectures are violated by KKLT. At least they are apparently violated. It's difficult to actually explicitly check if they are violated or not, because there are very few examples of ADS, supersymmetric ADS KKLT vacua, if any, actually. And it is satisfied, they are both satisfied by the large volume scenario, actually. So that's what the situation in terms of string theory is. And then let me just mention a connection to other ideas that have been going around. There is a CFT dual interpretation of these conjectures. So in particular, alpha equals a half means there should be no parametric gap between the dimension of a finite and an infinite number of operators in a CFT dual. And at the same time as our paper came out a few days before, there was also an interesting study from the CFT perspective on this question of whether you can have separation of scales. And it was suggested that something like the strong version of our conjecture may be related to the presence of gauge symmetries rather than supersymmetry. So that would be something interesting to think about. And there is implications for de Sitter vacua. In particular, the distance conjecture suggests that you should not be able to have an effective theory where you have a potential and a continuous family of minima of this potential that you can move from ADS continuously through Minkowski up to de Sitter. Because if you try to do that, as you go towards Minkowski, you should find an infinite tower of massless states becoming massless and ruining your effective theory. So you should not be able, in the same theory, have some continuous family of vacua going from ADS to de Sitter. So this could be important. And of course, if our universe is de Sitter, then it suggests that there should be a tower of states at 10 to the minus 120 times this parameter alpha and Planck. And this might have very interesting signatures, because even if we don't know what this order 1 alpha is, even if it's, let's say, 0.1, then it still tells you there should be tower states at 10 to the minus 12 and Planck, which is still a very interesting possibility. So to summarize, I discussed a number of swampland conditions on light towers of states. So when we might expect that string theory leads to light towers of states, There are two rather famous ones, the weak gravity conjecture and distance conjecture, that I talked a little bit about what the evidence for them is and what could be the physics underlying them. And then these are connected to two other conjectures that I discussed, the spin-2 conjecture, which is essentially the weak gravity conjecture applied to the Stuckelberg U1 field inside the massive spin-2 field, and the ADS distance conjecture, which is essentially the distance conjecture, but applied not to internal metric variations, but to external metric variations. And that's it. Thank you.
Any questions for Eran? Yes.
KKLT should have many non-supersymmetric ADS vacua. How do these things fit with the conjecture?
So non-supersymmetric ADS vacua should only satisfy the weak version. Sorry. So if it's non-supersymmetric, we propose there should be some order 1 power here. And as I said, KKLT implicitly violates both the conjectures. So if it's really true that you could have arbitrarily small W0, like the proposal for our universe W0 could be 10 to the minus 100 or something, and you can really realize the KKLT scenario, then in principle, there are KK modes associated to the 4 cycles, but they're only logarithmically sensitive to the cosmological constant, not power law. So in that sense, it violates it. But it could be that it is satisfied in the sense that going to small W0 may force you to go to some limit in complex structure moduli space, let's say like the conifold limit, where you might get a long throat and then get light towers of states. But it's very difficult to check because there are no explicit constructions of small W0s. So it's impossible to check, essentially. Yeah.
I'm sorry, I didn't understand some of the details very well, but you did suggest a connection between the radius of the internal space and of ADS space.
Yes.
And what was not clear was whether you wanted the scales to be the same or for your conjectures, or whether you could allow a parametric separation between them. I thought you were saying that's ruled out, but my question was mass, and you referred to this, but massive 2A, as you know, has non-Freud-Rubin compactifications. And there's a parametric separation of scales. So how does that fit in with what you said?
Okay, thank you. So first of all, the weak version of the conjecture, if you like, says that they can be parametrically separated in the sense that if alpha is smaller than a half, then you can have parametric separation of scales. But still, you would get an infinite tower of massless states when lambda goes to 0. And these type 2 vacuums satisfy this, but they violate the strong version, which says that if it's supersymmetric, then it should be a half. So as I mentioned, there are these vacua, these ones here, which are type 2A on a Calabi-Yau with flux. But it's been known for a long time that these are vacua in the 4-dimensional effective theory, but they are not 10-dimensional solutions. They do not solve the 10-dimensional equations of motion. So we can discuss more about that later if you want. So if our conjecture is true, then if these are uplifted to full 10-dimensional solutions, then they would actually see that the separation scale goes away.
People have written down effective theories of massive spin 2, whose breakdown scale is intermediate between Planck and graviton mass. So you are saying they are all in the swampland. Is this correct?
If it depends. So, good. So, yeah, I mean, I would say that if these towers of states are not there, then we claim they are in the swampland. And in fact, this breakdown theory, this is the strong coupling scale for the case when the spin 2 is like a graviton. So in the sense that it couples to the energy momentum tensor. And then there's a kind of a back reaction effect which leads to this breakdown strong coupling scale, which is m squared m Planck to the 3rd. And in fact, if our conjecture is correct, it would tell us that this scale is actually a fictitious scale. Because the scale where we say these these towers of states appear is m, which is before m squared m Planck to the 3rd. So if our conjecture is correct, it would say that this strong coupling scale is a fictitious scale, because if you realize this theory in quantum gravity, if that's possible, you will see that before you hit it, you will hit an infinite tower of states, which will change your theory.
So there is no effective theory then, because if things break down at M, there is never any effective theory.
Okay, good. So the strong one tells you there should not be an effective theory for a massive graviton, a single massive graviton. It should be, that massive graviton should always be the first in a whole tower of states set by the SEM mass scale. On the other hand, there are things like bigravity theories, for example, where you have a massive graviton and a massive spin 2 field, and then this MW doesn't have to be the Planck scale. So if you can make MW much smaller than the Planck scale, then you see you can make this tower much heavier than the spin 2 field. And then that's okay. So we say you can have an effective theory of a massive spin 2 particle as long as its interaction strength is stronger than gravity. So for the graviton it doesn't work, but in other cases it may be possible. That's what the conjecture says anyway.
Okay, so let's thank Eran again.